Computer. Okay. Congratulations. I figured it out.
Okay. Okay. So basically, the title here is modeling the COVID-19 in Colorado. The reason I chose this title with the all models are wrong, but some are useful. There's a sort of a well-known quote by a statistician, George Box, from several years ago. All models are wrong, but some are useful, basically. And so the whole point of this is that yes, we know that every model we have has some features that could be improved, but it is particularly helpful to understand well how the information propagates through our assumptions about how contacts happen, infections happen, and what that can tell us in terms of predictions about the pandemic. So. Okay, so we have the talk we've broken up into three parts. How did we get here? Where are we now? And where are we headed with this this particular once in a century event that everyone in the world now seems to be aware of what the word coronavirus means and COVID-19. So, how did we get here? So this is just a recap of the timeline, just to sort of it's difficult. It's easy, at least, well, for me, it is easy to get caught up in the every day. There's something new coming out, but to keep a perspective of how things transpired. The first infection was back in mid-November, as far as a phylogenetic analysis can confirm. That person did not die, but they had an infection, and you can sort of trace this back using the sort of genetics of the virus. So late December in Wuhan, some physicians in a hospital there realized that they had a cluster of pneumonia-related diseases, acute respiratory distress. One of them died. By the 2nd of January, 41 cases. 13th, there was the first case out China was reported. And then on the 17th, this is the Imperial College in London, has a mathematical epidemiology group head by a guy by the name of Professor Ferguson, who is sort of one of the world leaders in mathematical epidemiology. And they started issuing reports on this particular pandemic and trying to estimate the size of it, how it was going to spread, and projections forward. I think they're up to report 14 or something by now. But, so there's been sort of a steady stream of predictions there. So very quickly, you're seeing 571 cases in 25 provinces in China. So it's sort of growing quite spectacularly. There was a huge jump. Then going to 3 days later, first European case, 1,900 confirmed cases worldwide. Then on the 30th, it jumps. First US case is confirmed. We're up to 7,700. And then basically, if you look at the timeline for February, pretty much, it's not that nothing happened. It's just that the entire month is nothing but first case in this country, first case in this country, first case in this country, sort of indicating that this has really become a very worldwide and deserving of the word pandemic. Closer to home, Colorado reported their first 2 cases in March. This is started as a cluster with my understanding was that in the ski resorts was sort of where this started coming from. Just a few days later, as we're all aware, we moved online to instructions. And the 8 days after that, the governor closed all bars, restaurants, theaters, large groups of people. And then one of the results of this was there was an incredible surge in the sales of guns, toilet paper, and hand sanitizer. I don't know what that says about Colorado or American society, but I thought it was an interesting piece of information. So then on the 25th, the governor decided that to implement a stay-at-home order for basically a month, and that just got lifted this week to go to a safer at home order. And the purpose of this, of course, was to target more susceptible populations, encouraging them to stay home based on the demographics that we understand about who gets infected and who ends up having very serious cases and symptomatics. Okay, so that's where it all that's what would happen in the last few months that we're all been living through. Okay, so what I thought I'd start off with here in the beginning was to describe really where a lot of the mathematical modeling came from, and it goes back to the 20s and the early 30s with these two physicians basically in the UK, 27, 32, and 33. And what they did, that their model in the original papers was much more sophisticated. It was actually an age-structured PDE model. But at the end of the day, when they wanted to do computations, they could simplify it to multiple categories. And that was sort of really their big contribution, was to take a population and say, let's break this up into this compartmental framework where we have a certain subset is susceptible, infectious, and then they called it immune, but basically now we call it recovered. And so this is the basis of what we call the SIR model. And this is the ODE version of this, is just that you have a mass action infection rate. So there's some likelihood that S times S will be infected by I, and so you will lose the susceptible and they will become infected. So there's the flow between the susceptible compartment to the infected compartment. And you have the beta is the infection rate, basically the contact process. And you can scale it by N. Some people non-dimensionalize to get rid of the total population N. But in general, this is what it looks like. And then of course you have infectious category, and then beta over N SI is where it comes from, and then minus gamma I is where it leaves and goes to the recovered category. If you look at this model, of course, it's really, there's only one, actually if you look at the dimensions of it, you can simplify it to a one-dimensional ODE, but for the purposes of what we're going to talk about, the recovered variable is just sort of an observer variable. There's nothing that happens in that. It's all the dynamics of S going to I is really what's driving the entire process. So just to show you what a simulation looks like, this is what you see when you take that SIR model and say start with a population of 500 and put one infected in there. So you have 499 people that are susceptible and one infected. And at the end of the day, all this really is describing is a flow between compartments. And it's one way is the simple model that you start with. It just starts as susceptibles, flows to infected, and flows to recovered. And you see that here with this wave of infection, where the red curve sort of peaks around day 20 and then decays. And then the green curve, the greenish bluish, I guess on my screen, is the one that's showing that everyone is passing through the infected category. So fundamentally, there's not a huge amount that is, for the simple model, it doesn't have a huge amount going on. It's just a wave passing through that compartment. So as a side note, this semester I was actually teaching math biology, and we were doing this section on mathematical epidemiology. And usually, it's a simple ODE model. Everyone in there has had the differential equations class, and it's pretty straightforward. And the students were very, very attentive in this section of the course as we were going on talking about all of the implications of SIR models and such. Anyway, so just quickly here to sort of understand some of the language that's being thrown around in the newspapers. This is a phase plane between S and I, and the yellow curve here is a null line. So of course the black curve is the boundary of your domain because you have a total population. So either you can't be above this black curve in the upper right. So it's all the dynamics happening in the lower left. And so what you see here is in the lower right, that's the initial condition of 400 susceptibles and one infected. So right down there. And if you start with that situation, the curve goes up, passes through the null line, and then converges back down to basically the horizontal axis here is S is a line of equilibriums. Okay. So everything to the left of the yellow curve is a stable equilibrium. Everything to the right is an unstable equilibrium. And it is this distinction here that actually gives rise to the concept of the R naught, or the basic reproductive number in this context. How do you think about it in this ODE context? And so you'll note that if your initial condition is, again, to the lower left of the black line, if it is to the right of the null line the yellow null line, you will find that your number of infections goes up before it goes down. And that is, again, from the mathematical epidemiology perspective, that is the definition of having an epidemic. So if it goes up before it goes down, you've got something. If it just goes down, that means it's not the most, you don't have to worry about it in the sense of trying to come up with therapies and strategies and mitigation approaches. So that's how we think about it. Is this basic reproductive number as the infectious category increases, and this is the differential equation, when of course I is greater than 0 at your initial condition, and you can very easily figure out that that means that beta S naught over gamma n has to be greater than 1. And so that's what you end up calling the basic reproductive number for this ODE model. Depending, one of the things I will just note is if you non-dimensionalize things, sometimes the n appears, sometimes it doesn't. But this is basically it. You can also approximate it. You don't really need S naught over n, right? Because S naught is almost the total population if you have one infected. But I leave it in there because we'll talk about that a little bit later. Okay, so in the newspapers, if you see them talking about R naught, this is what they mean. Does infected go up? The other way to think about this is it's the number of susceptibles and infections will infect over their lifespan. Okay, so beta is the infection rate, and then gamma is the recovery rate, and so that ratio will give you the basically number of people that it's going to be infected over its lifespan when it spends in the infectious category. Okay, so obviously, if you have an R naught of 2, that means that somebody is infecting 2 other people, which of course leads to growth in your infectious population. Okay. One of the issues here, though, is this particular formulation is really only valid at the beginning of the epidemic, when you're talking about, what is the initial condition and such. And so tracking it in time, you have to be a little more subtle in what you're thinking about. And I'll talk about that in just a minute, but just keep that in mind that, if you have a point later in the epidemic where a large number of people have already been infected, a new infection is not going to infect the same number of people as if it was that one person way back in the beginning where everybody was susceptible. Okay, it's just sort of a numbers game. And so one of the ways that you can start to think about this is have an effective R naught, where you watch as the susceptibles change in time. And of course, if you just do the simple SIR model, you see that it sort of curves and goes down. And so late in the epidemic, you're not going to have that many people. A new infectious person is not going to infect a lot of as many as they would have, again, in a completely naive susceptible population. So if these types of concepts are of interest to you, Herb Heathcote wrote a very nice Science Review article about 20 years ago now, talking about all these different ways that you could take that basic SIR model and extend it in ways that make it more accurate. The one that in particular we're going to be dealing with is called an SEIR model, where you have an exposed category between the susceptible and the infectious. And this simply is exactly what it sounds like. Somebody is exposed, and so that the virus or whatever pathogen is in their body without them actually exhibiting symptoms or being able to infect another person. This is a framework, of course. You can include vaccines, and you can describe concepts of, maybe I'll talk a little bit about this, the herd immunity concept, where if enough people are inoculated and they're not susceptible, then your effective R naught can be so reduced that it's not a problem. You can also talk about quarantines. If you have sort of somebody goes into a quarantine and comes back out of the quarantine, these types of structures. It's just compartmental modeling where you have flow between compartments, but it's sort of, you can set it up in very standard structured ways. One of the things I have not seen any work on this as yet. I'm sure there's some people that are looking at it. There's passive immunity that a mother would pass to a child when the child is born, because they're going to have, if the mother has gotten a particular some sort of a disease, she's going to have antibodies flowing around in her bloodstream, which may be passed to the child, who's then going to be immune for some amount of time while they still have those antibodies before they decay. So, but then this is all, if you want, go read Herb Heathcote's paper. It's really quite nice. The one thing I will talk about just briefly here is there's this concept of reinfection, where if you connect the infectious category, instead of it flowing to the recovered category, it can go back to the susceptible category. This creates a situation where you can have an endemic steady state, where previously the steady states were basically 0 or the total population. You can have something between 0 and total population, and you can actually have, depending on your parameter choices, you can get bifurcations where you have oscillations and all sorts of other interesting types of behavior as you add more interesting compartments. But as far as we understand, and there was just most recently a report from South Korea that suggested very strongly that reinfection was not possible, and that some of those previous positive tests for people who had been infected were actually errors, and they were false positives because of sort of dead virus, non-functional, floating around in their bloodstream. So hopefully that's not something that we're dealing with like the common cold kind of a situation where we can get it again and again and again. Okay, so the Ferguson model. So this is the Imperial College model. So I just wanted to briefly touch on this because this is one of the things that really scared a lot of governments and started to promote them to getting into action. And basically, they did have a sort of an individual-based model. That's what they were using. I'll talk a little bit about that, what they're doing, but broadly speaking, is trying to answer the same question of how do people move from susceptible categories to infected categories and so on. And the reason that this had such a big impact, of course, is because of Imperial College's reputation and sort of shadow that they cast as far as what they do, and they were predicting 500,000 deaths in the UK alone, and over 2 million in the US. And this curve here really it tells the story of what's going on. So the red line is an estimate of the critical care beds that were needed. One of the lessons from China was that the people that came in who were really not doing well, they had to have ventilators if there was any chance of survival. If they did not get the ventilators and their respiratory system was really quite impacted, it was not a very good prognosis at all. That was it. And so you can look at this in the black curve here, of course, is the basically where it crosses that critical care threshold in number of people and goes well above it. And these are, basically per 100,000 of the population. So you're seeing quite a spectacular peak in the well, it would be deaths, basically, everybody above that red line. And so what they explored, of course, was, given that the math was indicating that this was coming, what could be done? Therapies, there hadn't been large-scale trials. There was not a lot known about what was going to work or not work. Obviously, there was no vaccine at this time in January when they were doing this, and so they had to look at non-pharmaceutical interventions. Closing universities and schools, household quarantine, general social distancing. These types of concepts came out of a lot of those early articles in January and February. And so what you see here is that one of the goals that you could basically try to keep that curve below the red line, right? There's going to be something passing through the population. Can you keep it below the red line? Or if you have in that sort of gray region, they say, okay, let's have some social distancing enforced. And maybe the orange curve is a little bit above it, but overall it's sort of hugging that and keeping it down. But the problem is that the moment that you release that social distancing, the dynamics of the problem don't change. It sort of continues to have a peak, right? And it's how many people have passed through the infectious category. And if you can push that peak later or keep it lower for a later time so that you can still maintain and have your critical care beds needed. Okay. So I'll come back to this, but I just want to say sort of the whole idea is if that sort of gray window there, the whole idea is to change the beta, the contact rate. And so if you look back at the model here, let me just go back to the ODE. So it's this beta right here. This beta would be a function of time. So it would be one number before there was any social distancing, and then in a window of time, like for Colorado, for basically the month of April, it was a lower number. Okay, but the problem is, of course, you release social distancing, and then it pops back up to the higher one, and you still have the same dynamics. It doesn't change anything. Okay. Okay. So how do we get even further along here? So mid-early March, the governor and the Colorado Department of Public Health and the Environment asked for a COVID-19 modeling team to form. And so this is the list of people that are on the team. I've primarily worked with Beth Carlton, who's an epidemiologist, and Andrea Buchwald and Katie Colburn. who are all sort of very, basically the researchers in epidemiology and faculty over in the School of Medicine and the School of Public Health. Um, and then, yeah, so those are the people that there's another sort of focus on this, and I'll talk a little bit about that, but that's not really the area that I've sort of focused on, and that has to do with the mobility questions. So when you do enforce social distancing, we can come up with an estimate of the infectivity and how that's gone down, but there's a real sort of interest in finding out what does that mean specifically for people, and how do they change their mobility habits, where they have some access to some cell phone data, and crunching those numbers to see how people have stopped going to large groups, reduce their trips, that kind of stuff. And that's Debashis Ghosh and Jimmy and Jude are sort of the primary people that are driving that. Anyway, so that's the list: the School of Medicine, CU Denver, Colorado State, and then a contact at the CDC. Okay. So that's where things came from, and so the question is, where are we now? Well, this is the status. We have this cumulative number of hospitalized cases in Colorado by date, and well, you can see sort of. So one of the things is you can kind of eyeball this, right? If you squint at it, you can kind of see around, late March, early April, it looks like we changed the type of growth. It went from exponential to linear, and then kind of maybe started to taper off in terms of the number of deaths. But it certainly, the number of deaths was not growing, the number of hospitalizations was not growing exponentially. One of the unfortunate implications of the way the disease works is because of the lags between infection and exposure, and then when somebody gets to the hospital or not gets to the hospital, whatever policy you put in place, it can take 2 weeks to see what the implication of that is. So there was this middle to late March is when those policies went into effect. Early April, that's when we're actually starting to see the implications of those and the sort of side of the benefits of those effects. So as you can see right now, this is trending these are the number, and you really are not seeing as dramatic increases in the number of hospitalizations, which is really quite a good thing, comparison with the total number of hospital beds in the state. You see a relatively similar trend in the cumulative number of deaths in the state of Colorado. So these are obviously it was growing exponentially back here. This is where it was a big concern, and then it's sort of linear, and now it's really starting to flatten. Flattening the curve is the phrase that's really popular. You've seen the news a lot. Yeah, so the social distancing is working. That's the take-home message, is that those policies that the governor implemented are really having the impact that we've been looking for. Question, of course, is moving forward, how do we make it sustained? Because the economy at some point we do need to deal with having people go back to work. So existing models, I just wanted to provide sort of an overview of some of the approaches that various states have taken and various organizations around the country and the world. The approach that we have focused on initially, partially because the feedback time for debugging and developing the model was relatively fast, was these deterministic SEIR model framework with some extra features associated with it. But there's a variety of other organizations. One that's very well known is the University of Pennsylvania has something called CHIME, which is at core an SIR model, but it's trying to describe how the specific impact on just hospitals is, people are moving through the hospital, but it's all just differential equations plus some statistics on top of it. Okay. There is also a purely statistical model from the Institute for Health Metrics and Evaluation out of the University of Washington. I'll talk about this one a little bit later. As from a bigger picture, they have sort of consistently projected, especially for Colorado, much lower projections in terms of infections here than pretty much anybody else. And we'll talk about some reasons why, but yeah, we'll get later. There is also a individual-based microsimulation model that the Ferguson group at Imperial College has used. There's also some Institute for Disease Modeling in Seattle as a big group. They're doing that. More of the agent-based modeling approaches. Yeah, so these are the things that are out there. And one of the things that has actually, there's been some wisdom taken from the meteorology and climate sort of literature, in the sense of they're using these ensemble approaches where you have very different model structures trying to make predictions, and looking at a sort of ensemble of these to say what they're happening. So you might use the IHME model to put a lower bound on what do you think the number of infections and deaths are going to be in your state. But yeah, so that's sort of, and I know that was at North Carolina, I think Illinois, and pretty sure California, and a few other ones are all sort of have this type of Texas have this type of approach. Okay, so let's just dive into it. This is the model that we have created for the state of Colorado. This was many of the versions, and the early ones was done by Dr. Buchwald, and the start with the susceptible, go to the exposed category, and this is where there's some subtleties here of as we know that people can be asymptomatic. That's a very common feature. There's widely varying estimations of what the asymptomatic versus symptomatic categories are. One of the strongest sort of an outlier that I saw was that all the women that were giving birth in New York City in one of the hospitals, they tested all of them for COVID, and the number of asymptomatic was something like 6-to-1 over the symptomatic, which suggests this huge number in the general population. That's sort of an outlier. It's not, so many of the other studies have shown less than that, but it's still, these numbers do exist and should be considered. Okay, so we have the asymptomatic and the symptomatic, and then of course the symptomatic, at a certain point, either the person is just mildly symptomatic and eventually recovers, or they end up needing hospitalization, which goes and needs a ventilator or does not need a ventilator. But pretty much, at least in Colorado, the main source of basically death was the becoming in the ICUs, and then either definitely on the ventilator, but still not surviving. And then we're assuming that they're going to the recovered and immune, and we're happy with the result from South Korea since suggesting that. So this is the actual mathematics, and it's not sort of super critical. There's basically, you see susceptibles, exposed, asymptomatic, infectious, hospitalized, critical care, and recovered. It's just the SEIR structure that I told you about earlier. The important thing to note here is, and there's a variety of ways that we're doing this, but this is really where the time dependence part comes in. That social distancing with like a heavy side function, it turns on at certain times at different levels. Like there was the first, we called it phase 1 of the social distancing, where you sort of said bans restaurants and bars, and then there was the stay-at-home order. So there's sort of two different ratcheting up of the levels of social distancing. The first one was we estimated at 45%, and the second one, depending upon when we were doing it, I think it was ranging between like 80 and 85% was the second one. But okay, so that's yeah, just but it's at the end of the day, aside from the initial infection event, these are all linear differential equations. So you have one mass action that is the initiation, and then things flow through the compartments, and you want to have some control over how the flow happens. That's the whole point of what's going on here. Okay, so one of the things that I thought might be interesting to talk about is the basic reproductive number when you have a system of differential equations. You can't just plot S versus I anymore, right? You have multiple infected, that exposed category. And so the question is, how do you try to come up with an estimate here? You can't do a simple phase plane analysis. And so how do you compute this? Well, so here's the way you do it. You consider all the compartments that have infections. And so this is exposed, infectious, and asymptomatic. And I should say all compartments with infection that can infect other people. Presumably, once you get in the hospital, personal protective equipment and all sorts of precautions are being taken so that someone who's in the hospital is not going to be infecting the staff at the hospital. That's our assumption. And as far as I understand, that's what's going on in the Colorado hospitals. So that, vector X and exposed, infectious, and asymptomatic. And so what we're going to do here is we're going to consider and break up the terms in the model. So the appearance of new, a rate for new infections in an individual compartment, and then the transition between the compartments. Okay, so it's not super complicated. It's just sort of how do you get new infections new infections that are not just coming from another compartment. So there's the script F is really that nonlinear terms. Is going to be a couple of those, the entries there having to do with the asymptomatic and the infectious, creating new exposed category individuals, and then just moving around. So you take the Jacobian, and so we're just linearizing it. That's all we're doing here. So you change it to a linear differential equation where you have two matrices F minus V. And what you can do here is you factor out a V to the right, because all that's doing is really moving the individuals around in different categories. And so now you have F times V inverse minus the identity. Okay. And so what this now does is it focuses our attention on this FV inverse, which is known as the next generation matrix. And you can look at the spectral radius of that and compare it with the spectral radius of the identity, right? Which is 1. And so all of a sudden now we're back in a framework that, or at least a computation that can be understood by saying, is it less than 1, equal to 1, or greater than 1? And this is how you will result in infections that are growing or decaying. So you can actually plot this, of course, as a function of social distancing, and you can see that you get a nice, straight line here. Of course, it's 1 minus social distancing times a bunch of other parameters and such. And the critical threshold is around that 80% mark. So if you can reach an 80% reduction in your social distancing social contacts that could have resulted in a infection event, then anything above 85% reduction will help the epidemic to decay and go away. Anything below, of course, is resulting in a higher R naught. And this is the curve for this bigger system, this SEIR system that we're using. There's been, I would say, a range of estimations of what the R naught is for this particular epidemic. In Colorado, our first initial pass at this sort of suggested that it was between 2 and 3 was the R naught. There have been groups that have estimated it as high as 5 to 6. So this disease is, looking at the dynamics, very contagious as the issue. Okay, so what do we do with this? I mean, this is nice and interesting, and it says, yes, there is some uncertainty associated with that 80% mark, right? I mean, there's uncertainty associated with everything here because we have, we're fitting to data to get beta. We know gamma pretty well, but many of the other parameters are actually fit parameters that are coming out of the estimation, and so there's some confidence, or at least we can, for different sort of initial ideas and estimations of these parameters, there's a region around 0.8. So maybe not 0.8 is exactly the number, but it's sort of in the ballpark. So what the take-home message here is that so first of all, just notice that beta over gamma S naught over N, that's the original R naught from the SIR model that we first talked about. So I'm going to replace that just with R naught. And then I'm going to look at what happens for varying what was the initial R naught of the infection, and to see what the social distancing you would need to get a spectral radius to be equal to 1. Okay, so the whole idea is if your original simplified dynamics before anybody knew anything about social distancing was, say, 4, that you could go up and say, well, I would need a social distancing above about 70% in order to reduce this epidemic. And the take-home message here, of course, is that for initial R naughts between 2.5 and 6, you still need something between 50 to 80%. So whether or not you have a precision about what that is, you need to make sure your social distancing is very high to reduce the epidemic spread. Okay. So moving on from this, the next sort of thing that has been an advance to the model as we got more data. I mean, one of the things to keep in mind is that it's not like we were able to set up a model back in March and then continue to use it. We got more and more information about the demographics of who was getting infected, how were they doing on the ventilators and not, and who was actually dying. And so what we were able to do, because those are hard numbers that tell you what is the rate of recovery for say individuals in certain categories. And so we ended up coming up with three different categories based on the statistics of somebody between 0 and 30 years old, 30 to 60, and then above 60. So we have basically a three age structure. So there's three copies of this SIR model, and really the red parameters there, that is what is really the difference between each of the categories of hospitalization rates, rates going into critical care, probability of being sort of having symptoms, these types of parameters. That was really that those were actually, we were able to, given the demographics of the populations that we had, we were able to get those, and we didn't have to fit several of them, so that we could go back to trying to fit beta and get the contact rate and how it had changed with the social distancing. Okay. And just as a side note, of course, you can derive the effective spectral radius for n age categories. It's actually an analytical computation that's relatively straightforward to do. So that can sort of be done, and we throw that in our analysis to show how the effect of R naught is changing as a function of time, or even just in the initial infection. So let's show some pictures, and you can see where things are. And these are the types of curves that really were the most convincing. When you try to discuss these concepts with people making decisions and stakeholders in the state, is that we're trying to fit based on the data that we have the most confidence in, which is of course the hospitalizations and the demographics of that. And we made some estimations and educated guesses about things, but at the end of the day, we're able to more importantly fit the data that's later on, right? And then you can see how the trends are happening, and you can project these things forward and say what's happening without social distancing, and then what's happening at 45% on the 17th. So this was an early fit we did that showed that it was really going to have a long-term impact of doing social distancing. And so here is what happened later. And this was this was sort of the way that it was requested in terms of kind of the uncertainty quantification was we'd like to know several different parameters to see how the spread is working. And this is the detected cases. And very quickly we were stagnating, which was really nice to see. And this was not a sort of a super, especially right around the beginning of April, the fit's not perfect, but it's really showing you that excuse me, that things had turned a corner, and that the social distancing was really, really working for the second phase when the stay-at-home order had been placed. So this is a very happy picture we're headed. So the question is, of course, where are we headed with this? Okay. And looking forward, this is the type of analysis that was most helpful for the governor's office and the CDPHE, the public health department, in understanding what the magnitude of how many hospitalizations they were going to be facing and critical care, and looking at moving forward from different social distancing rates. You can see that the peaks, the peak for the 80%, the 70%, those are really staying at the 2,000 bed count level, which I don't know what it's up to now. At one point, it was about 2,000 beds was the number that could be handled in the state. My understanding is they probably increased that by now. But questions of making sure that whatever the peak is stays below that number were pretty critical. And sort of understanding that it really does require high social distancing, and so that's why there's excuse me, more mitigation strategies in terms of masks and safer at home kind of orders to try to keep these effective social distancing impact on the beta lower. And you can see here that this is why we're not stopping these well, social distancing, is that, the moment you do, you get another peak, right? And that's one of the that's a feature here, is like, as long as there is nothing that has fundamentally changed about the disease dynamics, there's going to be a peak, and it will just happen later on. Okay. Let's see. So so one of the other things that we have been working to incorporate into the model is more precision about mobility, and there are some uh, basically mobility matrices that say, how much do specific age categories move in general, and how do they much do they interact with different age groups. And this is, I don't know if it's specifically Apple, but this was how I was able to get the picture for Colorado quickly. So what happened here, of course, is you can see the baseline for travel and driving using cell phone data, aggregated cell phone data. And it's, hovering around. There's peaks in different parts of the days of the week and so on. But then once the stay-at-home order gets put in place, it really drops down. But it seems like over time, it's started to creep back up a little bit. Maybe people anticipating the safer at home type of order. But this is the mobility team is the group that's sort of incorporating this. There's a reasonable way we're going to, it's just a mixing matrix that gets inserted into the differential equation model. And it seems to work out. We're getting some nice results with that moving forward. So. But this is one other feature that is sort of, there's the massive amount of data, and how do you parse this and maintain, anonymous ideas, and sort of tracking where people are going and trying to aggregate the information so there's no issues of privacy that they're working with. Okay. Okay, so those are the sort of features that we're trying to include. I just did want to make a brief mention about comparison with this IHME model, because it's something I've just seen in the news a lot. Like, even there was an interview with one of the directors of this, Chris Murray, on 538. If you follow Nate Silver's statistics, his sort of website for this. So one of the issues here is that if you dive down into the methods for this particular model, their approach is to assume a Gaussian in time. So the number of, this is, whatever these are reporting here, ICU beds, everything, it is at its core based upon an assumption of normal distribution in time for the number of deaths. And then everything else is leveraged on that core assumption, which is, there's, it's perfectly, it's a strategy one could use, and there are a lot of sort of statistical mitigations that you could do to sort of recalibrate your model as you move along. But it's still, at its core, it is symmetric around the peak. And so one of there's two issues with this model. This is sort of one of them, is that if you're using, say, the data from Wuhan, which is what they had previously, or even the data now from Colorado, you're going to assume that the number of infections will go up and go down in a mirror image. And if you look at the SIR model, the red curve there does not look symmetric, right? So there's a disconnect between these mechanistic types of models and this more statistical based model. The other reason that it's there's some suspicion about it is that they're actually drawing from a database at Hopkins, and the Hopkins database does not match up with the Department of Public Health database here. So there's sort of a couple of issues with this. I'm just bringing this up so that if you see this in the news, you can be a little more skeptical about whatever they're saying. But historically, they have been a pretty low on their estimates for the state. But because it's also a statistical model, it's very straightforward to get some of these uncertainty sort of clouds that you see, the sort of haze around the curves, which are really nice to get those. Okay. So the mitigation strategies that are moving forward, that the governor is sort of enforcing, and based upon the discussions that we have had and with the Department of Public Health and moving on up the chain, the safer at home order, and then the masks. And so this was an interesting result that I thought was something to share here. So this is from a preprint article that's talking about the relationship between the efficacy of the mask and the adherence. So whether or not you're wearing what is it, an N95 mask versus a scarf versus holding your hand in front of your face. How how effective is that versus how many people are actually doing that? And one of the things that you can note here is, of course, you want to be in the blue region because that is where your R naught is less than the one curve, and it takes some doing, right? You have to have an 80, more or less something above a good percentage there if you're going to have like 60% of the population adhering to it. You have to have, it looks like about a 70% effective mask. And so there's a trade-off there, and it really would be better if everybody was wearing the masks and they were good and effective masks to reduce this. So the question is, can you do this using masks in combination with other like safe at home type orders? That's sort of the mix of strategies that the governor has chosen to try to make sure that R naught is staying below one. Basically. Oh, and I was just going to say, it's one of the things that's been fascinating as you've learned about this is the yes, it's a preprint. Yes, it's a submitted article. Things are moving so fast that this is there's for lack of a better way to say it, there's simply not time to wait for the standard review process to happen. There was a article. There was a journal that I was, I think it was the radiology journal. Vanya was telling me that they were receiving something like 50 articles a day on this particular topic, and so the bandwidth for handling reviewing those things is just enormous. And how do you do that and get it through the process in a timely fashion? There's been a lot of sort of looking at preprints and posting things as sort of, because there's just some things are moving so fast that the science just doesn't, review process is not having the time to do the things. Okay. One of the other things that as we get better at detecting cases, contact tracing is something that the Department of Public Health in Colorado and elsewhere is really, this is the strategy. Once you flatten the curve, once you get the number of cases that are coming in every day below a certain threshold, and I thought it was 152 per 100,000 people or whatever, was that's the number of people you need to process every day if you are able to find out, their entire contact network they could have been in touch with. Okay, so the problem is that you have to have the cases low enough that you can actually have a chance of logistically of tracing everyone down and finding all those people and telling them to quarantine for 2 weeks or so. That's really the strategy of what the governor is pursuing here, is to make sure we flatten the curve and then ramp up the testing and tracing so that we can bring to bear, another weapon to reduce the infection rate. And so that's what's being hired and coming online right now. One of the things that I will mention this because I've also seen this as a discussion is that there's these questions of herd immunity, and I didn't really have enough time to put in a sort of full mathematical analysis of this in here. But what this is effectively is that if you have a sufficiently high percent of the population that is recovered or immune, the rates, like there's not enough susceptibles for the infectious to contact. And so there's an effective herd immunity. Usually it's 1 minus 1 over the R naught for the simple case, as far as the fraction of people that need to be sort of for having it be a herd immunity. But it's one of those things where the problem with this approach, if you just sort of let the infection wave pass through the population, is that you will basically break your medical system. It's just there are too many people who are susceptible and will experience catastrophic loss of life quickly if you try to use that strategy. So that's something that is not super exciting at the moment. So I thought I'd say some of the promising developments that I've been reading about in some of the articles that I've seen coming out. There is some strong evidence from South Korea that the previous reports that they had in terms of people being reinfected, those were actually false positives and just dead virus floating around in the bloodstream. And so they're, the public health, Ministry of Public Health, I think, just released a report saying they had no evidence of the coronavirus reinfection, actually. sorry, my tabbing got messed up a little bit here. One of the things that University of Chicago had some evidence that in using sort of nasal cannulas, those sort of oxygen concentrators that you see people with emphysema a lot, the hoses that just come into the nose, and the portable ones, those seem to be in the realm of the same level of effectiveness as ventilators, where you're just giving somebody high amounts of oxygen that's warm and humid, and that seems to actually, mitigate against what the virus is doing to creating pneumonia in the lungs. So that's a very positive development, of course, because then we don't need to worry about manufacturing huge numbers of ventilators fast, if that's actually, because there's lots of cannulas and lots of oxygen concentrators out there right now. Of course, you've probably heard in the news there's several promising medications that have started to becoming sort of, again, these are sort of preliminary studies, but they do suggest that a very strong impact from them. There's actually been some other sort of more widespread surveys of existing medications to see if they can come up with things. And there's a few in there that are also proving to be very effective. So there's actually some really promising drugs on a horizon of, sometime probably be in the next month or two, we're more aware of these. There's, of course, vaccines are being researched quite heavily. There's many companies that are doing this. Several of these are already in clinical trials. One in the UK has already moved forward. I don't know if there's any preliminary results on that one, but I've seen at least I think 3 that were in clinical trials right now. So what's our conclusions here? Well, developed a mathematical epidemiology, created, coded, validated, and added age structuring in less than a month, which that seemed impressive to have it done that fast. It was a lot of work by the entire team, but it really was it's quite impressive that it all came together. We can compute these basic and effective reproduction numbers for models of these various different complexities. And then these were, one piece of information, a big piece of information, but it was one piece of them that was used to inform decision-making at the state level. Acknowledgements. Governor Paulus for listening to the mathematicians and the epidemiologists and the rest of people. A sort of big thank you for the way that he's handled it. I think it's been very positive. School of Public Health, Department of Public Health and the Environment, and the entire COVID modeling team. All of these, really working in synergy to sort of try to reduce the damage to our to the state in terms of at all levels of health and the economy. Then other acknowledgements, Vanya for just discussions and excellent ideas and such, and then my 3-year-old Benjamin for being very patient when I've been on the phone far more than I should have, and also my graduate students for giving me the being very kind and not basically just letting me deal with this and try to push it forward and do the research on this angle. I have not paid as much attention as I wanted to you. And then of course also the math biology course students. I wanted to give a thank you to them and indulging me beginning of class. Every class I sort of did a little 10-15 minute digression on here's some new exciting things that's happened in the math of looking at this particular pandemic. All right, that's it. Questions? Hello?
Well, I can jump in if you don't mind. This is Keith.
Mm-hmm.
So thank you for the talk, my very nice talk, and explaining all the details that has gone into your intensive work on this effort. So we appreciate that you're represented us, and thank you for for the talk itself. Question about herd immunity. So you said this is sort of leads to catastrophic consequences, but you have nations like Sweden who have taken this approach, and yet you probably know more than I, but it doesn't seem to be catastrophic yet in that nation. Can you speak?
That's true.
Can you speak?
It's a good question, and I must admit that I downloaded the article talking about that and haven't read it. I know that there's a lot different in terms of the medical system and the contact tracing there, but I don't know what specifically was different about that. All I can say is that if the rates hold for Colorado and then basically we infected everybody in the state, that would be, what is it, like 2% of the population of Colorado would probably be dead. That's, I mean, if those numbers hold up. As far as Sweden, yeah, I saw an article making some explanations about why it had happened. I'm not familiar with that off the top of my head. I didn't read the entire article. So.
Okay, thank you.
Lucas had a question. Could excess deaths use to get maybe it's better if he says it, or you can read it. That would work as well. Can you, or do you have to fight?
Sorry, I had the, I just have I have full screen, so let me just chat.
No, I can do it.
Oh no, I got the chat up here.
Estimates of actual COVID mortality rates.
Excess deaths. What do you mean by excess deaths?
I think there's maybe people who are who have died at home and maybe haven't been counted.
Yes. Certainly. I mean, more information about that would be helpful. I guess. I mean, so the quick answer to your question is yes. Of course, if there was more information about that, that would be incredibly helpful to know, because presumably it would be a higher mortality rate if you got the people that were sorry, I'm seeing there's also a statement by Jimmy, undercounting by a factor of 2 in the U.S. So definitely, that would have a huge impact upon the mortality rate estimate. I guess the couple of the concepts that come to mind are, there's going to be a lot of sort of revision of these data, right? As we go along, going to go back and people are going to look and more closely at what happened and basically the deaths that happened, and if they were actually COVID-19 deaths or if that was some other natural causes or what have you. The other thing I would say is that one of the great things about having such sort of the high quality data from the Department of Public Health and knowing the people in the actual numbers that are high enough to sort of get a good sense of the study of that is that there's presumably some dynamics happening, and the longer that stays sort of as the same, the better chance you have at trying to estimate what those parameters are. So as it sort of goes along, if your parameters are time dependent, it's one of those things where that's another degree of freedom. If you say your parameters are changing in time, and that's a challenging thing to do as far as how many people, like say the percent of hospitalization is changing, like people are staying at home versus going in. We see the curve looks like it's behaving similar to what you would see from a math epidemiology curve, like a compartmental model, and we're matching that. So that's giving us a sense of the strategy and how effective the strategies are, and that's really what's the most important. And since we're able to fit that and match that data, and we can watch the curve go up and figure out where the peak is and see how it either stagnates or goes down, that's really what's the most important. But you're completely right. If we had better data on that would we would have a better idea of general mortality rates.
The same thing's true for like asymptomatic. Once we're able to test for antibodies,
yes,
we'll be able to have a better idea what those numbers are.
Yeah, right. I mean, right now what we're doing is, and there was actually a question about the data that we're using, and the data that we're using is, we have the number of people that are being tested, the number of positives, and then the number of people that are hospitalized, and the number of people that are going to critical care for ventilator needs. So, of course, there's what is the fraction of people that are being tested? What is the actual fraction of infectives in the population? because there's huge number of asymptomatics. That we've had to let be a fitted parameter. It's just something that we don't really have a good sense of what's the probability of being identified. But we do have a really good sense of how many people are in the hospital, right? And if we can leverage that and the deaths and the hospitalization and the critical care numbers to try to say how does that feed into a curve that then you're estimating the overall counts. That's why the curve seems to fit pretty well, is that we do actually have some high quality data that we're using. Let's see, let me go back to the other question.
Sorry, Nicholas Landry. Does your model assume homogeneously mixed?
The age structuring does not. It uses the mobility data for making an estimation. I mean, it started with the U.S. time use survey and analyzing how long people spent in various various places, like at the gym, at restaurants, grocery stores, that kind of thing. The model that we're using now does not assume sort of homogeneous mixing. There is an age, right now it's an age mixing. The data that we have, I don't, and maybe I see a couple of the mobility people are online here. I don't know if we have or if there's a privacy issue of getting contact and sort of heterogeneous mixing data on a finer resolution and making the model that much more fine resolution.
We're working on exactly that right now.
Sorry, what now?
I'm just saying, yeah, that's exactly what we're working on right now, is folding the mobility into the way we reconstruct those mixing. I mean, that is my role on the team.
Okay. Okay. The next question was about racial disparities in infections and deaths. There definitely is. On the top, I'm not familiar with the specific data. The data that we get from public health, I don't believe has that type of information. It might, but the data I have seen has not. So, I mean, maybe at some point that might be available. There's always questions of privacy, and you'd want to sort of make sure you respect that boundary also. So a question about from Nancy about the increases in domestic violence. I have been on a few calls where they discussed sort of domestic violence and sort of like child abuse kind of increases, but I don't know what the sort of strategy is to deal with that, or to even get an estimation of what the impact is. That's a very difficult situation, and trying to get that information is they're working on. I know there's several people that are sort of tasked with doing that. I just don't know much about it. So let's see. So there was sorry.
The disconnect between the social distancing percentage in the model and what it is in reality.
So one of the things to keep in mind is that we are viewing this through a very myopic lens of the contact and the infection rate, that beta. Okay, so we're calling it social distancing, but at the end of the day, it's the sort of impact of social distancing on the infection rate, and there's so many different ways that one could parameterize that. That when we went to fit it, we just called it the social distancing percent, but it's really the sort of decrease percentage in the infection rate. And that's really what it is. As far as like what it actually means for social distancing, trying to convince somebody that they really don't need to go to Home Depot as much as they should, this kind of thing. So I've heard stories about people, just saying, okay, well, now I can no longer, as it's now safe at home, I can now go shopping that I need to. So it's not as tight of a connection as one might hope.
Can you more specifically say, like, if your model comes up with you need at least 80% social distancing, how does the state decide, oh, that translates to closing schools, closing businesses, like that number? How do they interpret that number and implement it?
So I mean, I don't want to get into too much specifically what I mean, it's this was one of these things where we tried to provide the best information we could to the governor. And, as I said, things were moving very fast, and the best information was reduce the infection rate as much as you can.
All right.
That was the information that was provided. Moving forward, of course, there's teams that are doing economic analysis, right? Labor statistics, trying to look at that, and they have their own versions of thinking about social distancing and how does that impact various job markets. So all of these all come together, and then the governor ultimately has to make a decision about how to implement that and try to put it in place. At the time that I just don't how the level of precision of saying precisely what are the things impacting this. That's what's we're trying to tease out now. And that's what the mobility data team is part of working on, just teasing out all these different effects and how things are changing. I mean, just because people's behavior is changing, on a day-by-day basis based upon, what they read in the news and how safe they feel. If you have driven to the grocery store at all, there's been, a week or two difference. One time I saw everybody wearing masks the last time I went. And before that, there was a few people wearing masks, but so it's not as precise of a connection as we would hope, but it's definitely there's lots of people working on to try to make it more precise to say what's the special sauce of how much of this type of mitigation and how much of this type of mitigation should you try to enforce. Okay, let's see, another question from Thaisa. We have, I know they've chatted with Dan. I don't know. There's either, I think, a company that the state is working with to get this type of data. So I don't know if I don't think it's Facebook. I know that there has been contact between Dan and the mobility team. I don't know the extent of it, but they've definitely been talking to each other. It's one of those things where it's a great opportunity to have people who have expertise in some particular area to chip in and see. You try not to get too many cooks in there if there's already expertise in a particular area, but it's definitely we appreciate offers from many different fields if that's an expertise we don't have, especially. So is that answering your question, Thaisa?
I think Jimmy just mentioned that there's coordination right now between you guys.
That was my understanding. I don't know the extent of it. Let's see.
Can you talk about how you're dealing with bias in the data? Because we're undercounting the cases, so we're undercounting like death rates and hospitalizations and all of that. So if you look at strategies like herd immunity or stay at home or
so we're not undercounting hospitalizations, because basically everyone that's coming with any sort of symptoms is being is tested.
Sorry, I meant rate of hospitalizations, since you're only testing extreme cases mostly. The hospitalization rate appears higher than what it likely is.
I'm not sure. So the hospitalizations, I mean, that's sort of a hard number, right? We're getting that number directly from the Department of Public Health, and that's pretty. I mean, there's not a huge amount of bias in that.
No, I'm
delays. There's definitely lags, right? I mean, we have to. There's certainly some number of days before you can sort of say, well, I trust that data, right?
Not in the actual number, but in the rate. So if you're doing like transition between these states in the model, how can you like how are you accounting for not knowing the rate that somebody would transfer from being infected to becoming hospitalized if we're undercounting the total cases?
Well, so there's two things I would say. The first is that it's an effective rate of hospitalization. So there may be some fraction that could be hospitalized that we don't know, but it's sort of an issue of degrees of freedom there, right? We don't. It's not even really a sense of bias or anything. It's the effective rate that people are entering the hospital, and that's what we can try to fit. The second thing is that there is a parameter, the probability of identification, that is actually being fit, which is leveraging not the sort of hard knowledge of the cases in the hospitals and the sort of critical care hospitalizations. So when you sort of start trying to fit what you believe are the cases that the total cases that the state is reporting, you have the number of hospitalizations without critical care, the total number of hospitalizations plus some fraction of the actual number of infected. So there is a number in there that allows us a fudge factor wiggle room, right? I mean, it's trying to identify exactly what that is. The problem is, as you go along, presumably that number changes in time, right? As we get a higher and higher sort of testing rate. And so that's one of the reasons why it was very fitting when we had let me just pull back for a second. It's going to be up here. There. So that was one of the reasons why when the curve was coming through and we were fitting this, we weren't quite so worried about the curve being above those data early in March and then matching it later on, because our sense was that we were getting better at identifying those people. So there is it is being corrected for in some sense, but it is right now just the one factor of saying what's the probability of being identified. Let's see. So the next question, what timeline is fitted? So we're usually fitting it up until I think it's 6 days in the past. That's the most. That's our data that's accurate, or that we believe is accurate based upon reporting delays. There's all sorts of other quirks. Was it LabCorp dumped a huge number of test results like one day, and then later on actually said when those tests happened. And so if you looked on that day, it looked like all of a sudden there was this huge spike in the cases. But then the next day they revised it with the actual times that these things were reported, and then so that smeared everything out. And so it was So you do have to wait at least 5 or 6 days before you trust that the data that you want to fit is reasonable. And then projecting it forward, I mean, we've run, you run projections all the way until next year, right? To see, what's going to happen in a year's time. If we can make sure the peak stays below the bed counts, or, and then there's all these questions about what's going to happen if we have an in-residence university and, what is it, 30, 40,000 students from all over the world come back to Boulder. And bring whatever they
extension on that question, I guess, would be, have you measured how well you can predict, I guess?
In the sense, I mean, we've only had really basically a month, right? And sure. I mean, it's sort of one of those things where we're comfortable predicting, on the order of like a week or two. And the problem is that when you start doing these predictions, the governor makes a decision, and then your dynamics change. And so you try to figure out a way to, say, well, how well did we do based upon changing these parameters? Because then you have to wait and see what the data says about what was your fit and how did that work. Moving forward. So it's certainly not as clean as it would be nice to have, right? To say, let me fit this data, let me have a training set and then test it and this kind of stuff. It's not, it's much messier, because you try to make decisions based upon what you project forward and what you're trying to avoid as a catastrophic situation and say, June or July. Is that answering your question?
Yeah, I was curious in particular on the next slide.
Next slide. Oops.
Yeah. So it kind of seems like you've got, I mean, I can clearly see what's happening. I guess you show all these different trajectories. So kind of what I saw was it looked almost like you were fitting up until 317 and then showing possible trajectories forward. Is that what indeed is happening?
Let's see. I mean, the number of cases has been sort of stagnating. And I mean, I guess the better picture, let's go back to the earlier on. I guess these are hospitalizations, not the detected cases. I mean, it's the pictures that I have seen is that it is sort of continuing to hover around this region, maybe going up a little bit. So the question here, right, is, I mean, you see it seems to fit the curve very well when it's increasing, but then if you can call it a steady state, I mean, we don't have a curve that sort of turns the corner and goes down a little bit and then has a little bit of a, go up to hit that point at the end there. That's not really what the model is sort of set up to do. And so my understanding is that the red curve is kind of where things are sort of sitting, is that it's kind of, bouncing around in something that's sort of stationary and starting to drift down a little bit. That's just what my understanding. But the other problem, and the reason we didn't go, and the reports didn't go much past this, is that this is sort of around when the testing started to ramp up. And so it's sort of unclear if now you need to change your probability identification as that moves forward. So there's a bunch of sort of competing features so that are sort of thwarting you if you just can't keep using the same model moving forward because there's so much dynamics going on and changes in the parameters. Any other questions? Oh, let's see. It's the chat.
I didn't see any other ones pop up.
Okay.
I have a question. It's not on the plot about the mask. Is that, so they keep telling us the mask have, if it's coming, there's directionality in the effectiveness and so, or the effectiveness that people are talking about. So, right, the N95 prevents everything from coming in. And then they're saying that the homemade masks are going to reduce the amount that goes out.
Sure.
Is this plot, what is this plot reporting? Which is it trying to reduce the amount of coronavirus in the air, or is it you actually inhaling it?
My understanding is it's you inhaling it.
Okay.
That's what this is supposed to be.
Okay.
Yeah.
Houston has implemented mask. They've essentially opened Houston. Restaurants, museums. It should be interesting. And they're requiring masks. I don't understand how the restaurant works with the mask. And so
there's some interesting photos. I think it's in South Korea where they basically have plexiglass dividers, like on every single, like you have little cubicles on every single table. So you have your little sub part of the table that has a plexiglass walls around you.
They're going through a lot of Windex.
Yes.
All right. Unless anybody else has a question, I'm going to thank you for going way over and answering all of our questions. No, it's because people wanted. And Yes, this was awesome.
Yeah. No, there's a lot more that, you know, one can. I mean, the herd immunity mathematics, the uncertainty quantification mathematics. There's just I ran out of time when I was making the talk, so I was like, I can't put all this in here. So
Yeah, it's completely understandable. Yeah, no, it was awesome. Thank you.
all right. Well, thank you, and stay safe. And
Will do.
all right.
You too.
Thank you.
Oh.